We're about to step into the realm before that eruption, a place where nothing wasn't empty space, where time didn't flow, and where the very idea of existence collapses. In this strange territory, we'll wander through quantum foam seething with ghost-like particles, collide with endless branching universes, and glimpse mathematical structures so immense they make our cosmos feel miniature. If you're ready to challenge every assumption you've ever held about reality, buckle up. Let's begin. Imagine the final moment before moments existed, the literal boundary between before and when. Scientists called this point T0, an innocent name for the most violent transformation ever to occur. At this threshold, the concept of before loses all meaning because time had not yet been born. No ticking clocks, no aging, no sequence, not even darkness waiting to be illuminated. Only the absolute absence of duration. Here, our mathematics malfunction like a computer dividing by zero. Einstein's elegant equations, flawless everywhere else, simply collapsed into infinities. It's as if the universe posted a warning sign at its entrance in the language of physics: do not enter. And yet this forbidden moment is not merely the start of our universe, it's the birth of the very framework that allows beginnings at all. Before this instant, there was no arena for anything to happen, no dimensions to occupy, no space to stretch through, no time to advance. Trying to describe what existed before is like trying to explain the color of an object that has never encountered light in a place where light cannot exist. Our questions break because the tools we use, space, time, cause, sequence, were created by the very event we're asking about.
Still, modern physics hints that something profound stirred in this impossible nothing. Quantum mechanics tells us that even perfect emptiness can spark with brief flashes of energy, tiny blips that appear, vanish, and reappear endlessly. These fluctuations happen in the vacuum of space even now. And if they can emerge from nothing today, perhaps nothing was never truly nothing in the first place. One leading idea proposes that our universe began as one of these quantum flickers, except instead of blinking out, it detonated. In an unimaginably tiny fraction of a second, this speck of energy expanded faster than light, fabricating space itself as it grew. Picture a soap bubble forming on a perfectly still pond, but in this case, the pond doesn't exist, the surface doesn't exist, and somehow the bubble creates both as it inflates. The bubble becomes the pond becomes the world becomes everything. This phenomenon, known as cosmic inflation, explains why the universe looks remarkably uniform and why space appears strikingly flat. But it also leads to a wilder question. If a quantum fluctuation can spawn one universe, why only one? Mathematically, nothing suggests the process should stop after a single cosmic birth. Now consider this. When you empty a jar completely, is it truly empty? Most would say yes, yet physics says otherwise. What we perceive as empty space is actually humming with invisible motion. Even in the lonely stretches between galaxies, where you might find a single atom in an entire cubic meter, space itself is ablaze with hidden energy. This isn't the philosophical void humans have debated for centuries. This is an experimentally confirmed, measurable nothingness that refuses to be nothing. Scientists discovered its restless nature when they attempted to cool matter to absolute zero, to drain away every last shred of energy. Now brace yourself for the leap. If our entire observable universe began as a fluctuation in some primordial vacuum, what was that vacuum in? What set the stage for quantum fields to exist at all? This question pushes us toward layers of nothingness deeper than anything our physics can currently describe. Some physicists argue that mathematics itself is the ultimate foundation, not numbers on paper, but pure relationships that exist independent of the physical world. In this view, the universe is not built from matter or energy, but from patterns so intricate they manifest as reality. Others propose something even stranger, that consciousness plays a fundamental role. Quantum mechanics shows particles existing in multiple states at once until observed. So could conscious observation collapse possibility into the single reality we experience? And while you're reading this, particles are appearing and disappearing inside your cells. Not sci-fi imagery, but virtual particles, essential to the machinery of the universe. Every second, quadrillions of these ghost-like flashes are born inside you, live for fractions of a moment, and fade without leaving a trace. They might sound imaginary, yet they create real, measurable effects. They give electrons magnetic properties. They govern how light interacts with matter. They hold atomic nuclei together. Without virtual particles, atoms wouldn't exist. Chemistry wouldn't exist. You wouldn't exist. Think of these particles as cosmic credit cards. The vacuum lends them energy, they spend it by briefly existing, then repay the debt by disappearing. The shorter their lifespan, the more energy they can borrow. Some last just 10 to the minus 24 seconds, yet they can contain momentarily staggering amounts of energy. The quantum vacuum isn't an empty stage. It's a seething cosmic broth, constantly forming and dissolving ingredients. Virtual photons transmit electromagnetic forces. Virtual gluons hold quarks inside protons and neutrons. Every type of particle flickers through this invisible underworld. And here comes the twist.
Sometimes virtual particles become real. Pour enough energy into the quantum vacuum, and these particle pairs can separate before they destroy each other, effectively escaping into true existence. This happens near black holes. Stephen Hawking discovered that intense gravity can split virtual particle pairs at the event horizon. One falls in, the other escapes as radiation. The black hole loses energy, slowly evaporates, and in its final moments dies in a burst of light. This idea hints at something profound. If virtual particles can gain enough energy to become real, could the entire universe have done the same? Maybe the line between virtual and real is far thinner than we imagined. Maybe our universe is still borrowing energy from the deeper level of reality we haven't uncovered. In that case, everything, stars, galaxies, planets, people, might exist on cosmic credit in a fluctuation that began 13.8 billion years ago. But fluctuations like this wouldn't create just one universe. If the quantum vacuum has the power to spawn a cosmos, why would it stop at one? Nothing in the math suggests a limit. Physicists realize that the same vacuum teeming with virtual particles might be bubbling with entire universes, each its own expanding bubble in an infinite sea. Right now, as you read this, there could be countless versions of you doing the same in parallel worlds. Some universes differ by the position of a single electron. Others obey completely different physics. The multiverse wasn't invented as fantasy. It emerged as the natural consequence of quantum fluctuations. Each universe would ignite with its own Big Bang, inflate at its own speed, and evolve with its own laws. Stronger gravity, burning stars too fast to form life. Weaker forces, preventing atoms from forming. Sterile voids, or places where unimaginable forms of life might arise. Picture an endless cosmic ocean where every possible wave eventually rises. Our universe is just one of those waves, temporary, beautiful, but not unique.
The multiverse, if it exists, is as indifferent to us as the ocean is to a single droplet of spray. And yet the idea grows more overwhelming the deeper you look. Certain versions of multiverse theory propose something astonishing, an infinite number of universes, meaning that every variation of reality you can imagine, and countless you can't, unfolds somewhere. A world where dinosaurs never vanished. A world where gravity pushes instead of pulls. A world where you pursued a career in space exploration instead of reading these words. These aren't storybook fantasies. They drop out naturally from the mathematics of quantum mechanics and cosmic inflation. Solve the equations governing the quantum vacuum, and endless universe production becomes not speculation, but a built-in feature of reality. The implications are both beautiful and terrifying. If there are infinite universes, then every possible sorrow and every possible triumph is happening right now, somewhere. Every book that could ever be written already exists in some reality. Every scientific breakthrough imaginable has already occurred in countless parallel worlds. Some physicists take this logic even further, suggesting that the multiverse might itself be only one layer in an even vaster hierarchy. Infinite multiverses, each containing infinite universes, stacked in an architecture so immense our minds can barely form metaphors for it. But the strangeness goes deeper. If parallel universes are real, they may not remain perfectly separate. Quantum theory hints that universes might brush against one another, merge, influence, or even collide. Some researchers have proposed that faint scars or distortions in the cosmic microwave background might be ancient fingerprints of such collisions. Universe bumping against universe long before our galaxy existed. And this leads to a staggering possibility. Our Big Bang may not have been the beginning, but one beat in an eternal cosmic rhythm. Imagine a phoenix that reignites itself every trillion years. Some cosmologists believe the universe works the same way, expanding, slowing, collapsing, and exploding anew in a never-ending loop. In this model, the Big Bang wasn't creation out of nothing, but transformation from an earlier cosmic era. The cyclic universe picture suggests that our cosmos expands for billions of years, exactly as we observe today. Then, after unimaginable ages, the expansion halts and reverses. Gravity takes command, pulling galaxies inward, tightening space-time into a catastrophic implosion known as the Big Crunch. But instead of ending in final destruction, this inward collapse rebounds, igniting a fresh expansion in what appears from the inside like a brand new Big Bang. Time doesn't stop. It simply passes through a cosmic bounce, like a universe falling onto an elastic trampoline and leaping upward into a new cycle. Each bounce births a universe that looks young and fresh, even though it's just one oscillation in an internal heartbeat. This idea solves several challenges in traditional Big Bang theory, such as the universe's remarkable uniformity without requiring a burst of faster-than-light inflation. It also sidesteps the unsettling question of what triggered the first Big Bang. In cyclic models, there was no first. There were only cycles. Current observations suggest the universe's expansion is speeding up because of dark energy, which seems to prevent a future big crunch. But supporters of cyclic cosmology have adapted. They propose that the strength of dark energy might evolve over cosmic timescales, eventually shifting from expansion driving to contraction driving. In some versions, each cycle lasts about 1 trillion years. If our current cycle began 13.8 billion years ago, then by cosmic standards, we are infants with hundreds of billions of years to go before collapse begins. And these cycles may not be identical. Tiny variations could accumulate from one universe to the next, allowing evolution not just of matter, but of intelligence itself. Some theorists even suggest that information could leak subtly from one cosmic version to the next, letting future cycles inherit traces of earlier ones. Other cyclic ideas imagine a cosmos where universes take turns, expanding and contracting like pistons in a massive multidimensional engine. While our universe spreads outward, others compress. While others ignite in fresh Big Bangs, we drift calmly through our expansion era. In this mechanical view, the answer to what came before our Big Bang is simply another universe's final breath.
But this only shifts the mystery upward. Who or what wound the spring of eternity in the first place? And can the cycles ever truly end? Now the picture becomes even stranger. According to string theory, reality might hide 6 extra dimensions, tightly folded around every point in space. You're surrounded by them right now, invisible, untouchable, but ever present. Think of a garden hose seen from far away. It appears as a simple one-dimensional line, but zoom in and you discover it has a curled circular dimension wrapped around it. String theory claims our universe works exactly like that, except instead of one hidden dimension, there may be 6, compacted at scales too tiny for any microscope to detect. What we think of as 3 dimensions of space plus time might actually just be the visible surface of a world with 10 or 11 total dimensions. These hidden dimensions are not empty. They shape how the fundamental forces behave. The curvature and twisting of these extra dimensions determine the strength of gravity, electromagnetism, and the nuclear forces we observe. In string theory, the smallest building blocks of nature are not particles, but minuscule vibrating loops of energy called strings, so tiny that if an atom were enlarged to the size of the solar system, a string would still be smaller than a leaf on a single tree. Each vibration pattern creates a different particle. An electron is one mode of vibration, a photon is another, quarks yet another. It's a cosmic orchestra in which every fundamental particle is a different musical note played by the same instrument. And now string theory connects back to our origins in a breathtaking way. The Big Bang might have been triggered by a collision between enormous higher dimensional sheets called branes. Our entire universe could be one such 3-dimensional membrane floating through a higher dimensional space, like a soap film drifting inside a vast multi-dimensional bubble. When 2 branes collide, the impact floods each one with unimaginable energy. From inside one of these branes, from our perspective, that energy release appears as a Big Bang, a sudden birth of time, space, and matter. But the branes themselves existed long before the crash. This brane collision model explains many mysteries about the universe's early uniformity and suggests the Big Bang wasn't creation from pure nothingness, but a phase change, a shift from one brane state to another. The hidden dimensions might even house parallel branes, each hosting its own universe. These parallel worlds could be mere fractions of a millimeter away in higher dimensional space, yet forever unreachable because we are confined to our own dimensional sheet. And this leads to something even more astonishing about cosmic creation.
Somewhere in the vastness of the cosmos, new universes are igniting into existence every single second. While you've been reading these words, countless new Big Bangs have erupted in remote corners of reality, each one inflating into a cosmos containing billions of galaxies. This isn't fantasy. It's the natural conclusion of eternal inflation, one of the most successful and mathematically supported ideas in modern cosmology. Standard inflation describes how our universe ballooned from subatomic size to astronomical proportions in a tiny sliver of time after the Big Bang. But eternal inflation proposes something far more dramatic. Inflation never truly ends. It simply shifts from region to region, spawning an endless cascade of pocket universes within a constantly expanding multiverse. Imagine a pot of boiling water. New bubbles constantly appear, swell, and detach from the surface. Each bubble is a universe. The boiling water beneath is the inflating energy field that permeates the multiverse. Our observable universe is just the interior of one such bubble. The Big Bang wasn't the birth of everything. It was the moment when our local bubble ceased inflating and slowed to the expansion we measure today. But beyond our cosmic horizon, the inflationary field continues growing exponentially, endlessly generating new universes. Even if inflation began at some moment in the past,
once it starts, it produces infinite future space and infinite future time. The multiverse expands so quickly that no matter how many universes form, it always has room for infinitely more. And each pocket universe may obey entirely different physical rules. Some may have gravity so strong that stars collapse as soon as they form. Others may have forces so weak that atoms can't assemble. Most would be sterile wildernesses, but once in a while, the physical constants line up just right and complexity, chemistry, and even life emerge. Yet these bubble universes are separated by expanses of space that inflate faster than light can travel. Even at light speed, you'd never reach another universe because the distance between you and it grows faster than your ship could ever bridge. And here's the truly brain-twisting part. In an eternally inflating multiverse, every possible universe exists somewhere. One where faster than light travel is possible. One where time flows in reverse. One where physical constants lead to black holes to evolve into sentient objects. If eternal inflation is correct, then possibility and reality become indistinguishable. Everything that can happen does happen, somewhere. This leads some scientists to worry that eternal inflation predicts everything and therefore explains nothing. Others believe it is the cleanest, most elegant answer to why our universe appears so precisely tuned for life.
But even eternal inflation slams into a deeper wall, the beginning itself. Physicists can trace our universe's history back to an astonishingly early moment, a fraction of a fraction of a fraction of a second after the Big Bang. They understand when atomic nuclei formed, when stars ignited, even when space first became transparent. But there's a final barrier they cannot cross, a moment where the math self-destructs, a veil called the Planck epoch, stretching from time 0 to roughly 10 to the negative 43 seconds. During this unimaginably tiny interval, the universe was so hot, so dense, that gravity itself behaved quantum mechanically. Space and time became grainy, jittering like pixels in an overmagnified image. Below the Planck length, 10 to the negative 35 meters, distance becomes meaningless. Below the Planck time, 10 to the negative 43 seconds, the very idea of before and after breaks apart. Trying to measure anything in this regime would be like using a ruler made of atoms to measure something smaller than an atom. The tool itself becomes the limitation. Physics fails because every equation assumes a pre-existing stage where space and time already exist. At the Big Bang, there was no stage. The stage itself was being built. Einstein's relativity predicts that everything compresses into a point of infinite density, a singularity. But infinities usually signal that a theory has reached the edge of its usefulness, not that reality truly contains infinities. Quantum mechanics hints that this singularity should instead be replaced by a state of maximum density, where space and time are quantized, like energy levels inside an atom. But without a complete theory of quantum gravity, we can't yet describe this realm with confidence. Some physicists argue that asking what happened before the Planck epoch is like asking what's north of the North Pole. Time itself may have a boundary, a first instant, unprecedented by anything. Others suggest time might be emergent, a property that arises only when enough quantum systems interact, just as temperature only exists when enough atoms vibrate together. In this picture, the deep structure of reality might be timeless, with time appearing only as a collective illusion. This brings us to one of the deepest puzzles in existence, the origin of information. Before the universe began, where did the information needed to describe it reside? Every atom in your body encodes astonishing detail: energy levels, spin, quantum states. Your DNA carries biological information.
Your neurons carry thoughts and memories. Stars, galaxies, particles, all of it is structured data. Even a simple hydrogen atom contains highly specific information about the electron's orbit and spin. Multiply that across every atom in every star across every galaxy, and the information content of the universe becomes incomprehensibly vast. Traditional physics treats information as something encoded into matter and energy. But quantum mechanics flips this idea. Information may be more fundamental than the matter and energy that hold it. The state of a quantum particle determines what the particle is, not the other way around. And that leads to a profound paradox. If the universe emerged from a quantum fluctuation in empty space, where did the information of that fluctuation come from? An empty vacuum shouldn't contain the encyclopedic level of data required to generate billions of galaxies. Some scientists suggest information like energy can never be created or destroyed, only transformed.
If information can never be created or destroyed, only transformed, then the information that defines our universe must have existed before the Big Bang in some form. But this immediately raises an unsettling question. Where was that information stored when space and time themselves did not yet exist? One idea points to the holographic principle, a concept that completely overturns our intuitions. It states that all the information inside a three-dimensional region can be encoded on its two-dimensional boundary, much like a hologram that produces a full 3D scene from a flat sheet. Applied to the cosmos, this suggests that all the information in our universe may be inscribed on the cosmic horizon, the farthest observable boundary of space-time. In that case, everything we experience, matter, motion, even ourselves, could be nothing more than a projection from data stored on a distant 2D surface. We might be living inside a cosmic hologram without realizing it. But even this breathtaking idea skirts the deeper mystery. Where did the boundary information originate? Some theorists argue that information is the most fundamental ingredient of reality, more basic than matter, energy, or space-time. In this view, the universe behaves like a vast computational process, and physical reality emerges from primordial information being processed in ways we don't yet understand. If information is truly fundamental, then asking where it came from is like asking why mathematics is true. It simply is. Our universe would be one possible arrangement of this eternal information, chosen by mechanisms that remain hidden from us. This information-first picture leads to an even shockinger suggestion. True nothingness may be impossible. Imagine what most people think of as absolute nothing. No matter, no energy, no fields, no laws, no space, no time, no possibility for anything at all. Quantum mechanics says such a state cannot exist. The culprit is the uncertainty principle, the rule that forbids perfect knowledge of certain quantities, including energy and time. In a perfectly empty region with truly zero energy, you would know that energy precisely. The uncertainty principle forbids this. So even the emptiest emptiness must fluctuate. These fluctuations have real consequences. Virtual particles appear, flicker, and vanish. The stronger the fluctuation, the shorter its lifespan. But for a brief instant, virtual energy can create miniature, temporary realities. And now comes the staggering leap. If quantum fluctuations can occur in empty space, then they can occur even without space. Even pure nothingness, if such a thing could exist, would be unstable. It would foam with fluctuations because uncertainty still applies. Nothingness is not a blank void. It is a restless sea of potential. And the uncertainty principle allows enormous fluctuations if they happen quickly enough. A fluctuation large enough to create an entire universe is allowed, as long as it repays its borrowed energy almost instantly. Here's where quantum inflation changes everything.
If a universal scale fluctuation inflates extremely fast, it can grow larger than its own quantum wavelength before the repayment time expires. Once that threshold is crossed, the fluctuation becomes permanent. It transitions from borrowed existence into real existence. It's like a quantum credit card with no spending limit but instant repayment rules. Most purchases vanish immediately, but occasionally one becomes so large that the system can't cancel it. The debt becomes real, and so does the purchase. Our entire universe may be one such runaway fluctuation, a quantum hiccup that expanded too quickly to be erased. And if one universe can emerge this way, then countless others could be forming constantly. Pure nothingness, if it ever existed, would explode into endless somethings.
This brings us to a profound question. If nothingness is impossible, has something existed forever? And that leads directly to consciousness. For nearly a century, quantum mechanics has revealed a disturbing fact. Before measurement, particles exist in multiple possible states at once. But the instant they're observed, those probabilities collapse into a single outcome. The act of observation helps create reality. Electrons pass through multiple paths simultaneously until we check which path they take. Photons behave like waves until we measure them, then freeze into particles. The quantum realm remains undetermined until awareness looks at it. But then we face an impossible question. If observation creates reality, what observed the universe before conscious beings evolved? How could the cosmos exist for billions of years before minds appeared to collapse its quantum haze into concrete events? Some physicists have suggested a radical answer. Consciousness may be fundamental, not an emergent property of matter, but something woven into the fabric of existence from the start. In this view, the Big Bang wasn't merely the birth of energy in space-time, it was the moment when cosmic consciousness first looked inward and crystallized itself into a universe. Reality becomes a vast quantum computation with consciousness acting as the processor that turns possibilities into actualities. Without it, the universe would remain pure probability, an uncollapsed cloud of potential. In this interpretation, before the Big Bang, there was nothing but pure awareness, infinite potential, with nothing yet to be aware of. The Big Bang was the moment when consciousness observed itself, and in doing so, created the framework of space, time, and matter. If consciousness shapes reality, then different forms of consciousness might create different realities. Human consciousness molds the universe according to how we measure and perceive it. Alien minds with entirely different cognitive structures might collapse quantum possibilities into universes bearing no resemblance to ours. This idea opens the door to parallel realities born from conscious choice. Every decision, every observation might split the universe, each branch representing another path consciousness could take. Some interpretations of quantum mechanics propose that all possible realities exist simultaneously, but consciousness selects the branch it experiences. Before the Big Bang, all universes existed as pure potential. The first conscious observation chose one, bringing it into definite form. If consciousness is fundamental, it might be the one thing that requires no origin story. It simply exists, as eternal as mathematics itself. In this view, the universe is consciousness, exploring its own infinite possibilities through the medium of space, time, and matter. And this leads to a final and even more radical idea. What if reality is literally made of mathematics? Everything you see right now, these words, your chair, the air around you, might not be physical in the traditional sense. According to the mathematical universe hypothesis, the world is built from mathematical structures so intricate that they have become self-aware. You're not made of atoms and molecules.
You're made of equations that learned to think. And this is not a metaphor.
MIT physicist Max Tegmark argues something astonishing. Mathematical existence and physical existence are the same thing. In his view, every photon, every electron, every quantum field is not just described by mathematics, it is mathematics. We don't model the universe with equations, we uncover the equations that the universe literally is. Think of what mathematics really represents. When you use algebra to describe motion, you aren't creating an approximation, you're revealing the underlying structure of reality. The equations aren't describing something else, they are the thing itself. In this picture, physical objects are simply mathematical structures complex enough to interact and self-organize. And suddenly, a centuries-long mystery dissolves. Why does mathematics describe nature with such uncanny perfection? Because reality is mathematics. We aren't inventing mathematical models of the universe, we're discovering the mathematical architecture that constitutes existence. But here's where the idea becomes emotionally overwhelming. If our universe is a mathematical structure, then every logically possible mathematical structure also exists as a physical universe. There are universes where geometry itself is different, where space has 4 spatial dimensions instead of 3. There are universes where the constants of nature take on radically different values, crafting alien forms of physics. Every theorem, every equation, every consistent set of rules corresponds to a universe somewhere in the full mathematical landscape. Our cosmos is just one pattern in an infinite library of patterns. From this viewpoint, the Big Bang wasn't the creation of matter from nothing, it was the moment when one particular mathematical structure became complex enough to support observer moments. Consciousness, your consciousness, is what it feels like from the inside when mathematics becomes self-referential and self-aware. You are not a biological organism experiencing a mathematical reality. You are a mathematical pattern that woke up. And now the ultimate leap. Before the Big Bang, all mathematical structures already existed, timeless, complete, infinite. Our universe began the moment observers arose within one specific structure, the moment the mathematics we inhabit became aware of itself. In this view, time is not fundamental. All moments exist simultaneously, fixed in a timeless mathematical object. We perceive time only because we are embedded within a structure that encodes temporal sequences. Subjective experience, consciousness, is simply what complex mathematics feels like from the inside. This leads us directly into the most baffling mystery in modern cosmology. Dark energy, the force tearing our universe apart, should not exist. In 1998, astronomers discovered something shocking. The universe's expansion wasn't slowing down, it was accelerating. Something was pushing galaxies apart. They named this invisible driver dark energy, and it now appears to make up 70% of everything. But dark energy behaves unlike any energy we understand. Normal energy thins out as space expands, like perfume diffusing in air. Dark energy does the opposite. The more space expands, the stronger dark energy becomes. The leading explanation is the cosmological constant, a term Einstein added to his equations to keep the universe static. He later called it his greatest mistake, but accelerating expansion suggests he stumbled onto a truth deeper than he realized. The cosmological constant represents the energy contained in empty space. Even a perfect vacuum has energy, and this vacuum energy applies a repulsive force that expands space itself. But here's the nightmare. Quantum mechanics predicts vacuum energy should be 10 to the 120th times larger than what we observe, the single worst prediction in scientific history.
If quantum mechanics were correct at face value, the universe would expand so violently that atoms couldn't form, stars wouldn't ignite, and galaxies couldn't exist. Yet somehow the vacuum energy in our universe sits tantalizingly close to zero, but not exactly zero. This fine-tuning is like balancing a pencil on its tip for billions of years during an earthquake. Something is adjusting the cosmological constant with impossible precision. Possible explanations. Dark energy might not be vacuum energy at all, but some unknown field. Physical laws may evolve over cosmic timescales. Or the multiverse offers a selection effect. Among infinite universes with random constants, we naturally appear in one where life is possible. But each explanation reveals deeper mysteries. Why is our universe tuned for complexity, for consciousness, for beings capable of asking these questions? Some physicists propose that observers themselves, through quantum measurement, help select which version of the universe becomes real. Consciousness might participate in tuning the constants of nature. This suggests a co-evolution of consciousness and cosmos, each shaping the other. Meanwhile, our universe may be quietly colliding with others right now. Eternal inflation predicts that our cosmos is just one bubble in an infinite cosmic foam. Most bubbles drift apart faster than light, but occasionally two bubbles form close enough that their boundaries touch before expansion rips them apart. These collisions don't obliterate galaxies, they're incredibly gentle. Subtle ripples of gravitational waves spread through both universes. Their signatures may be hidden in the faint microwave afterglow left behind by the Big Bang. We might already be looking at scars from ancient universe-to-universe contacts and not even realize it.
If another universe has ever brushed against our own, the evidence would appear in the oldest light in existence, the cosmic microwave background, the faint afterglow of the Big Bang spread across the sky. A collision would leave behind a nearly perfect circle, a subtle warm or cool patch like a bruise imprinted on the fabric of space-time itself, marking the moment when another reality made contact with ours. Several scientific teams have claimed to detect such circular scars in CMB maps, though others argue they could be nothing more than statistical noise or quirks in the instruments. The signals are faint, ambiguous, and nearly lost in the background hum of a 14-billion-year-old cosmos. We may already be staring at the fingerprints of parallel universes, but we can't confirm it yet. If these collisions are real, they may not be isolated events. As our cosmic bubble expands through the multiverse, it could have brushed against multiple neighbors. Our sky might contain several collision signatures, each one a silent reminder of a brief encounter between our universe and another. But the implications run far deeper. If universes can collide, they might also be able to exchange information across their shared boundary. Quantum fields could carry data from one cosmos to another during the moment of contact, creating the faintest form of interdimensional communication. Some physicists speculate, cautiously but seriously, that consciousness might have the ability to tunnel across these boundaries. If consciousness is a quantum process, as certain theories propose, then collisions between universes could create short-lived bridges linking the subjective experiences of parallel selves. This might explain the uncanny déjà vu sensations or strange memories of events that never occurred. Perhaps your consciousness occasionally receives faint echoes from alternate versions of you living in universes that briefly brushed against ours. And the possibilities don't stop with individuals. Entire civilizations in neighboring universes might attempt to use these collisions as communication channels, encoding signals into the quantum fields at the boundary. The cosmic microwave background could contain hidden messages sent by advanced beings trying to speak across dimensional divides. Someday, our technology might become advanced enough to detect those messages, or even send replies.
All of this becomes even more staggering when we consider a separate but related idea. Your entire reality might be a projection from a distant boundary. As you look around the room, experiencing a vivid three-dimensional world, you may actually be perceiving a hologram, a projection of information stored on a two-dimensional surface billions of light years away. This is not speculative fiction. It is a serious scientific model backed by deep theoretical work and observational clues. The idea traces back to black holes. Physicists realize something impossible. When matter falls into a black hole, it seems to vanish forever, yet the information about it must survive because quantum mechanics forbids information destruction. The answer was revolutionary. The information doesn't disappear. It spreads out across the black hole's two-dimensional surface, encoded in microscopic patterns. From the outside, the complete history of everything that has ever fallen in is stored on the event horizon. This revelation led to a profound generalization. If a black hole's entire three-dimensional interior can be described by data on its surface, then perhaps any region of space, including the entire universe, can be encoded on its boundary. Applied to cosmology, this means the entire observable universe, galaxies, stars, atoms, and even your thoughts may be information encoded on a distant two-dimensional cosmic horizon. We perceive three dimensions because that is how the information is rendered. But the true fundamental reality may lie far beyond our reach, written on a boundary we can never access. Think of watching a movie. The characters appear to move through a 3D world, yet the story is encoded on a flat screen. In the same way, our universe's rich complexity may emerge from quantum information spread across a distant surface. This holographic framework sheds new light on several deep mysteries. It suggests that space itself may be an emergent phenomenon, arising from patterns of quantum entanglement in the boundary information. Distance in our world corresponds to how strongly different regions of the boundary are entangled. It also offers a new way to understand the Big Bang. If our world is a holographic projection, then the Big Bang marks the moment when the boundary began processing and projecting information, not the creation of matter from literal nothingness. Before this projection turned on, the boundary might have existed in a dormant state, holding all the potential of our universe, but not yet expressing it. Some interpretations go further. Consciousness may be part of the projection mechanism, actively converting boundary information into perceived reality. Observers are not separate from the hologram. They are part of the system that renders it. This leads to an almost mystical conclusion. If reality is holographic, then the division between self and universe is an illusion. Every conscious being could be a different facet of a single information processing entity, experiencing itself from countless vantage points. And finally, we arrive at the most unsettling idea of all. Time itself might not exist at the deepest level of reality. Right now, you feel time flowing one moment after another, like beads sliding along a string. But this sensation may be an elaborate illusion created by the brain as it processes information in sequence. At the fundamental level, reality may be timeless, a complete structure that simply is, not unfolding, not progressing, just existing, all at once.
On a strip of film, every frame exists at the same time. It's only when the frames are run past the light in rapid succession that we perceive motion, the illusion of flow. In the same way, all moments in the history of the universe may coexist simultaneously in a timeless realm. Consciousness might create the sensation of time by experiencing these frozen moments one after another, giving rise to the illusion of a moving present. This idea emerges straight from physics.
Einstein's general relativity treats time as just another dimension, no more special than length, width, or height. In the four-dimensional block universe, your past, present, and future all exist together. Your birth, your final breath, and every moment in between are fixed into the geometry of space-time. Quantum mechanics takes an even more dramatic stance. At the quantum scale, events don't unfold in a definite order until they're observed. Particles can exist in superpositions of earlier and later states simultaneously. The quantum world lives in a realm where sequence does not exist, a universe suspended in pure potential. Only when consciousness observes does this timeless fog crystallize into a linear timeline we call experience. Some physicists propose that time itself arises from quantum entanglement. As quantum systems connect, they create patterns of correlation that form the arrow of time. The past is simply the direction of less entanglement. The future is the direction of more. And the present is the shifting frontier between the two. In a timeless reality, there is no before the Big Bang, because before implies sequence. All possible moments, including those we label as before creation, exist simultaneously within a larger, timeless structure. The Big Bang might not have been the birth of time, but the birth of temporal experience, the point when entanglement became rich enough to make time feel real. Before that, reality may have existed as a vast, timeless quantum superposition of every possibility.
Here, consciousness becomes central. The sensation of time may be simply what information processing feels like from the inside. The brain constructs a flowing present by weaving together memories of past states and predictions of future ones. Time isn't something you travel through, it's something your mind generates. Different forms of consciousness might therefore experience time in radically different ways. An artificial intelligence processing information along unfamiliar pathways might perceive time in a way humans could not imagine. Advanced alien civilizations, with neurological architectures unlike ours, may have learned to bend or manipulate their subjective temporal flow, speeding it up, slowing it down, or stepping outside of it entirely. If time is emergent rather than fundamental, then the question, what happened before the Big Bang, dissolves. There was no before. There was only timelessness until consciousness stitched the illusion of sequence onto the universe. This brings us to one of the strangest and most controversial ideas in cosmology. Why does the universe seem perfectly suited for observers like us? The anthropic principle begins with a simple observation. We exist. Therefore, the universe must be compatible with our existence. This sounds trivial, yet it leads to unsettling implications. The weak anthropic principle states that we can only find ourselves in a universe where conscious beings can exist. Universes with impossible chemistry, non-existent stars, or unstable atoms would host no observers, and thus no one to notice them. But the strong anthropic principle pushes far deeper. It suggests that the universe must possess properties that make consciousness not just possible, but inevitable. In this view, the constants of nature are not random, they are required to support life. This raises disturbing questions. Did the universe know that conscious beings would one day arise when its constants were set in the instance after the Big Bang? Or are observers somehow involved in selecting the constants in the first place? Certain interpretations of quantum mechanics propose that conscious observation does more than reveal reality. It selects which reality becomes actual. If so, then the existence of conscious observers might explain why the constants we observe are exactly those that permit consciousness. Imagine every possible universe with every possible set of constants coexisting in quantum superposition. Only when conscious beings rise does one branch become selected, the branch where consciousness can exist. A cosmic selection effect operating across time. The participatory anthropic principle takes this to its limit.
It proposes that conscious observers do not merely select which universe they experience, they actively participate in bringing the universe into being through observation. Reality becomes a partnership between quantum possibility and conscious choice. Neither exists independently of the other. Critics argue that anthropic reasoning is unscientific because it cannot be tested. If observers can only exist in observer-friendly universes, then by definition we cannot directly observe any other kind.
The anthropic principle eventually drifts into a realm where science and philosophy begin to merge. Critics argue it becomes unfalsifiable, an elegant explanation that cannot be tested, and therefore falls outside the boundaries of traditional science. Supporters counter that anthropic reasoning does make predictions. If a multiverse exists, then the laws of physics in our universe should lie close to the edge of what allows complexity, and that's exactly what we observe. Gravity, electromagnetism, nuclear forces, and the cosmological constant all sit at values so precise that even slight deviations would destroy the possibility of life. The anthropic view also predicts we should find ourselves in a typical universe among those that permit observers, not in an exceptionally fine-tuned outlier. Whether or not these arguments are persuasive, the debate forces us to confront unsettling questions. Are conscious beings cosmic accidents, emerging by chance? Or are observers somehow woven into the architecture of reality? The answer may determine whether consciousness is a rare flicker in an indifferent universe or an inevitable feature of existence itself. Yet beneath all philosophical speculation lies a much more immediate threat. Our universe may not be as stable as it appears. The quantum vacuum around you seems calm and unchanging, but it may be a false vacuum, a metastable state poised to collapse into a lower energy true vacuum. Imagine a ball perched at the top of a hill. It looks balanced, but the slightest disturbance will send it rolling toward the valley below. If our vacuum is that ball, then one day, spontaneously or triggered by some extreme event, it may tumble into a state where the laws of physics are rewritten. The danger stems from the Higgs field, the quantum field responsible for giving particles mass. Current measurements suggest the Higgs field might be resting in a metastable configuration, stable for now but not absolutely secure. Should it decay, the transition would unleash a bubble of true vacuum that expands at the speed of light, erasing all known physics in its path. Inside this bubble, particle masses would change. The forces could behave differently. Atoms might be impossible. Chemistry might cease to exist. And because the bubble wall travels at exactly the speed of light, we would receive no warning. One moment, the world would be normal, the next, gone. Worse still, vacuum decay might have already started somewhere in the universe. A bubble could be hurtling toward us at 186,000 miles per second, completely undetectable until the instant it arrives. Fortunately, the probability of vacuum decay under normal conditions is extremely low, possibly lower than one event in the lifetime of the universe. Yet certain conditions could accelerate the process. Ultra-high energy particle collisions, extreme gravitational fields near black holes, or exotic processes we do not yet understand. Some scientists worry that advanced particle accelerators could accidentally trigger decay, but others point out that cosmic rays routinely smash together at energies far higher than anything we can produce. If vacuum decay were easily triggered, the universe would already be gone. Still, the possibility forces profound questions. Could advanced civilizations, billions or trillions of years in the future, find ways to survive such a transition? Could they encode themselves into matter stable under the new physics, or escape into regions of space-time where the false vacuum remains intact?
Our cosmic origin story may hold clues to our cosmic fate.
Every model of pre-Big Bang physics offers a different ending. If we came from eternal inflation, we may return to it. If we're part of a cyclic universe, expansion might reverse into collapse. If we inhabit a metastable vacuum, annihilation may come without warning. And above all of these possibilities looms dark energy, the mysterious force driving the accelerated expansion of the universe. Observations suggest 3 radically different futures. 1. Heat death, eternal expansion. If dark energy remains constant, galaxies drift apart until stars die, black holes evaporate, and only cold particles remain, scattered across a frigid, eternal void. 2. The Big Rip, cosmic disintegration. If dark energy increases, expansion will accelerate uncontrollably. Eventually, it will tear galaxies apart, then solar systems, then atoms, and finally space-time itself, ending everything in about 22 billion years. 3. The Big Crunch, cosmic collapse. If dark energy weakens, gravity may regain dominance, halting expansion and pulling everything back into a final collapse, potentially triggering a new Big Bang. But these classical predictions might overlook something fundamental: consciousness. If consciousness plays any role in collapsing quantum possibilities into definite outcomes, as some interpretations suggest, then the survival of observers may influence the future of the cosmos itself. Far future civilizations may face choices that shape the destiny of reality. Allow consciousness to fade, leaving a universe of pure quantum possibility, or preserve awareness indefinitely, perhaps by transcending biology, or even engineer new universes, manipulating the quantum vacuum itself. The boldest theories imagine a self-consistent loop, consciousness in the far future influencing the conditions that allowed consciousness to arise in the first place. The universe becomes a closed causal structure, where the beginning and the end reflect each other across time. If this is true, then solving the mystery of what came before the Big Bang may depend on what conscious beings become at the end of time. And now we approach one of the deepest truths of all. Everything that ever happens may be recorded forever. Every moment you experience leaves its imprint on the quantum fabric of reality. Every photon entering your eye, every neural firing, every movement of every particle encodes information into space-time. According to the principle of information conservation, information cannot be destroyed, only transformed. Burn a book, and its words do not vanish. They are redistributed into the swirling dance of smoke, ash, and radiation. In principle, if you could track every particle, you could reconstruct the book perfectly.
Even black holes, long believed to destroy information, cannot escape this rule. Stephen Hawking once believed black holes obliterate information forever, shredding the fundamental rules of physics in the process. But later work, including insights Hawking himself helped develop, suggests the opposite. The information that falls into a black hole becomes encoded on its two-dimensional surface and slowly leaks back out as Hawking radiation during evaporation. If that is true, the implications are staggering. It means that every event in cosmic history, every quantum fluctuation after the Big Bang, every thought generated by every living mind, every vanished civilization, is preserved somewhere within the universe's quantum informational structure. Reality is less like a fleeting sequence of events and more like an eternal library of everything, containing perfect records of all that has ever been and all that could be. We may not yet possess the technology to read this cosmic archive, but the information remains, indestructible, merely transformed.
This also means something profound about the beginning of the universe. If information cannot be destroyed, then whatever existed before the Big Bang must, in some form, still be present within the quantum fabric of the cosmos. The pre-Big Bang state didn't vanish when our universe ignited. It metamorphosed into the initial conditions of our space-time. The oldest relics of the cosmos, the cosmic microwave background, primordial gravitational waves, and early quantum fluctuations may already encode echoes of whatever reality preceded our own. A sufficiently advanced civilization could someday decode these signals, effectively watching the pre-cosmic universe unfold like a documentary from a previous epoch. Information conservation has an even startling consequence. Consciousness itself is a form of information. If information can never be erased, then something about your thoughts, memories, and awareness might persist forever, written into space-time's quantum ledger. Far future technologies might allow civilizations to retrieve, reconstruct, and resurrect these patterns, restoring minds from the deep informational strata of the universe. This possibility connects directly to the deepest mystery in physics: how observation collapses quantum possibilities into definite outcomes. Quantum mechanics tells us that, until measured, particles occupy multiple states simultaneously. An electron does not spin up or down, it spins in every allowed direction at once until someone observes it. But no one knows why observation triggers this collapse. The Copenhagen interpretation simply declares measurement causes collapse the same way we accept the speed of light: fundamental, unquestioned, unexplained. But this leaves the key issue untouched. Why should consciousness possess this extraordinary ability? The many worlds interpretation tries to sidestep the problem. It claims that all possible outcomes occur, we simply perceive one branch of an ever-splitting multiverse. But this raises new puzzles. Why do we experience one definite branch and not the full superposition? What determines which branch consciousness inhabits? In solving one mystery, many worlds creates an infinite forest of others.
Some physicists and philosophers have suggested a radically different approach. Maybe consciousness itself is fundamental, not a product of matter, but a force that helps shape reality. In this view, quantum collapse is not a passive process. It is an interaction, a dialogue between conscious observers and physical possibilities. The universe becomes a joint creation, woven by quantum potential on one side and conscious selection on the other. If awareness is primary, then the earliest universe, long before living minds emerged, was a realm of pure, undetermined quantum possibility. Nothing was yet actual. All histories coexisted in superposition. The first spark of consciousness, in any primitive organism, would have precipitated a transformation. Like crystallization in a supercooled liquid, consciousness would retroactively choose one consistent cosmic history from the sea of possibilities, solidifying the universe's timeline from the Big Bang onward. This idea becomes even more astonishing when extended into the future. Advanced beings might learn to perform quantum observations that reach backward in time, selecting or reshaping cosmic history to ensure their own emergence. In such a self-consistent loop, consciousness at the end of time would influence conditions at the beginning. The universe's origin and its destiny would be entangled in a single, timeless relationship. From this perspective, solving the riddle of what came before the Big Bang may require conscious beings who survive until the very end, until they understand their role in the cosmic cycle. Now, we reach one of the deepest truths hinted at by modern physics. Everything you do leaves a permanent imprint on reality. Right now, this moment, your eyes moving across these words, the neural sparks in your brain, is being etched into the quantum state of space-time. Information conservation means these traces can never be erased. They can only be transformed, redistributed, encoded in new patterns. Burning a book may destroy its pages, but
but not the information they contained. The details melt into the motions of smoke particles, the glow of heat, the dance of photons. In principle, if you could track every particle, you could reconstruct the entire text. The same is true for black holes. For decades, they were thought to annihilate information, but research now indicates the opposite. Black holes preserve information on their surfaces and return it through evaporation. If even black holes, the universe's most destructive objects, cannot erase information, then nothing can.
Trillions of years from now, long after the last star has burned out and the final black hole has evaporated, when the universe is stretched so thin that lone particles drift billions of light years apart, what will be left? Most physicists would answer nothing, or something as close to nothing as reality permits. But what if nothing itself can evolve? Even in the far future, the quantum vacuum will persist, a seething sea of virtual particles, zero-point energy, and quantum fluctuations. This emptiness isn't barren. It's alive with possibility, capable of spawning entire universes through quantum tunneling. As the universe approaches maximum entropy, the vacuum may undergo radical phase transitions. New forms of nothing could emerge, each with different abilities to generate new realities. In a sense, the vacuum might learn, drifting toward states that produce universes hospitable to complexity and consciousness. Imagine evolution operating at the level of nothingness, random fluctuations that manage to create rich, long-lived universes might subtly bias the vacuum toward generating similar fluctuations later. The nothing that follows our universe could be better at producing something than the nothing that came before.
This process could continue endlessly, each cosmic generation giving rise to more sophisticated forms of emptiness. Eventually, the quantum vacuum may become so refined that it produces universes intentionally structured to support the rise of consciousness. Far future civilizations, surviving the cold death of starlight, might even learn to influence this process. Instead of waiting for random fluctuations, they may discover how to encode information directly into the vacuum, programming the creation of future universes. If consciousness persists into this post-cosmic era, it could merge with the vacuum, imprinting awareness into the bedrock of nothingness itself. Future nothing may not be empty. It could be conscious nothing, aware of its own potential, capable of choosing which realities to actualize. And that brings us to the most extraordinary possibility of all. If conscious nothingness can deliberately create universes, then the Big Bang itself might have been an intentional act, a creation chosen by an intelligence that evolved in a previous cosmic cycle. The nothing that preceded our universe may not have been blind emptiness, but a luminous void aware of its own capabilities, selecting this reality for reasons far beyond our comprehension. This forms a perfect circle, the deep future and the distant past merging into a single eternal feedback loop. The question, what came before the Big Bang, may only be solvable by conscious beings who survive until the end of time and discover their role in creating the beginning. Perhaps the most profound truth is that something and nothing, consciousness and cosmos, beginning and ending, are not separate. They are facets of one continuous creative process that transcends our present understanding. We set out to answer the impossible, what existed before the Big Bang. And the journey has carried us through quantum foam rising with virtual particles, through multiverses spawning realities without end, through the possibility that consciousness itself may be the fundamental creative engine of existence. We've learned that nothingness may be impossible, that time may be an illusion, and that our universe may be a holographic projection of information stored on a distant cosmic boundary.
These ideas sound stranger than science fiction, yet they emerge directly from our most successful theories. Quantum mechanics reveals that even empty space boils with energy. Cosmic inflation suggests universes are born endlessly. String theory uncovers hidden dimensions wrapped around every point in space. The holographic principle implies our universe is fundamentally two-dimensional, and information theory hints that consciousness may be woven into the core of reality. But the deepest insight is this: the question itself may be flawed. Asking what existed before the Big Bang might be like asking what lies north of the North Pole, a question that dissolves once we understand the true nature of space-time. Yet this doesn't diminish our search. By pressing against the limits of the knowable, we glimpse the profound unity between mind and cosmos, possibility and actuality, nothing and everything. We see that consciousness may not be an accident of evolution, but a co-creator of reality, a participant in the unfolding of the universe. If quantum measurement depends on observers, then each moment of awareness may be an act of creation, shaping the universe in ways we do not yet understand. If the multiverse exists, then every decision we make may fracture reality into countless branches, each one explored by a different version of ourselves. These ideas offer humility, showing us how little we truly understand, and hope, by suggesting that consciousness may endure far longer than stars or galaxies. The ultimate answer to what existed before the Big Bang may only be found by the conscious beings who live to the end of time and learn how consciousness and reality create each other. Until then, the mystery remains and deepens. The universe began in mystery, and it continues in wonder. We are not outside observers of this mystery. We are the mystery becoming aware of itself. In seeking the beginning, we join the eternal dance between something and nothing, possibility and actuality, question and creation. The journey continues, and with every question we ask, the universe becomes that much more aware of itself.